All right. Good morning, good afternoon, good evening, everyone, wherever you are in the world. Welcome to our ChemDraw Connect webinar series. My name is Nicolas Tribelot. I'm Director of Drug Discovery Chemistry at Revity Signals, and I will be your moderator for this session. This ongoing ChemDraw Connect webinar series is an opportunity for you to learn about ChemDraw's features, to effortlessly create eye-catching professional graphics that make your research shine. It is also an opportunity to explore digital technologies beyond ChemDraw, to invite guest speakers and engage with you on the capabilities you would be interested in having in the future. Today's topic is Beyond Retrosynthesis, AI-powered reaction design. A couple of housekeeping questions before we jump in. This session is being recorded and will be available for streaming at revitysignals.com/chemdraw-connect. Please submit your questions during this session through the questions panel located at the top of your screen. If you're interested in trying the AI tools presented today, please stay connected at the end. A small survey will be launched and you will have the opportunity to securely send a message to our guest speaker. As attendee, you will also receive an email after our ChemDraw Connect with links to the recording and to the same survey allowing you to liaise with our guest. As always, we want to hear from you. If you have any topic suggestions for our upcoming connects, feel free to reach out to us on signals.events@revity.com. Now, I'd like to introduce our speakers for today. Dr. Alex Clark is a classically trained synthetic organometallic chemist who got hooked on software engineering from an early age. He's been building tools for computer-aided drug discovery since 2001. From small molecules to proteins, 2D to 3D, interactive workflows to low-level algorithm, he's most at home in the domain of cheminformatics. Anything that involves a chemical diagram is interesting. In 2010, he founded Molecular Materials Informatics, a company dedicated to bringing cheminformatics to a broader range of chemical disciplines and computing platforms. Now I'll hand over to Alex, who will introduce you to the topic of today's webinar.
All right, thank you for the introduction and welcome everyone. I'm going to jump right into it because I've got a lot of content to talk about. So in the scientific literature, we have millions upon millions of well-described chemical reactions, such that for pretty much any organic compound you want to make, chances are the information you need to get it done is out there somewhere. So it's completely reasonable to expect software to be able to deliver this information to us when and where we need it. Now, one of the examples of where this does already work is the area of synthetic planning, and there are a number of really excellent tools out there which can really help you with figuring out what reactions you're supposed to do to achieve a particular product. But when it comes to figuring out how to actually do any of these reactions, you immediately find yourself at the state of the art. And so what I'm going to talk about for the next 40 minutes or so is a novel reaction recommendation engine which has the goal of filling out the scheme and providing a lot of details, starting with just the bare bones reaction. And then if I have any time at the end, I'm going to show a sneak preview of a prototype design tool for helping out with reaction optimization. Okay, so the typical starting point for the reaction recommendation is when you have the just the starting materials in the product, and maybe you have some other ideas about the reaction, but most other things are up for grabs. And this is also typically the starting point that you'll get if you're using a synthesis planning tool. So you just basically what you put in, what you want to get out, and then the goal is to figure out as much as you can about the reaction before you write it up as an actual procedure. So I want to define an idea that's a running theme throughout this presentation. It's the idea of the completed reaction scheme. So basically it's what you would put into ChemDraw if you were in the mood to be particularly thorough. So that's in addition to the starting materials and products, you also need to indicate any reagents, solvents, catalysts, and adjuncts that are also going into the reaction. You should at very least provide the time and temperature for the reaction, and then ideally, the reaction should be atom mapped on both sides. If possible, you should provide all of the formal byproducts, and everything in the reaction should be balanced. And so this is the idea of a scheme that is done, and then after this is all filled out, then it's time to go and write that up as an actual experiment and take it off to the fume hood. Okay, so now I'm just going to switch to live demo mode. And so I'm just going to briefly go through this tool just to show you that this is actually a real thing. So we start out with a blank page. The quickest way to get going is just to hit this demo button here. And that's filling in a very basic reaction, just 2 starting materials and 1 product. And it's also activating the recommendation engine in the background. So you saw that took a couple of seconds to come up with all of these hopefully helpful suggestions, which are shown as panels on the bottom half of the screen. And so the first suggestion that it has is an atom mapping. So I'm just going to accept that. I'll just switch the view, and you can see that the atoms have numbers associated with them, and that correlates the atoms on both sides. So it's a fairly standard thing to do with the reaction. But notice particularly that there are some of these atoms are highlighted in green. And these are parts of the core transform. So they're atoms that change state when they go from the reactant to the product. And that's a special marking, and we'll come back to that later for the model building. Now, there are atoms left over. If we look at the overall atom balance, there's an H and a bromine. And you'll see also here that the next recommendation is a byproduct. And this is basically the easiest prediction you can possibly do. So we can just fast accept that. And then there's another mapping operation which just fills in the byproduct, maps that to the appropriate reaction. And so that's basically going through and figuring out all of the stoichiometry for the reaction. Everything that changes state in the reaction is now done. And so we can then move on to the more high value calculations. And for the catalysts, which are done next, the first is a filter to decide whether or not we need a catalyst or not. And then there's a number of possible catalysts that we can select from. And so I just brought up the list on screen. Now, the highest ranked catalyst is a little bit dull, it's copper bromide. So we'll pick something slightly more interesting for the demo. This is a combination of a palladium pre-catalyst and a diphosphine ligand, which are added separately. So if I just save those, it's now added both of these components into the reaction scheme. And also my recommendations have disappeared because I selected an alternate choice. So I'll just send it back in and get back to where we started. And here we are with all of the rest of the recommendations. So the next one is the solvents. That's a very similar process for catalysts. Dichloromethane is the top ranked, and that seems legit to me. So I'm just going to fast accept that. And now the last recommendation is this exotic looking diagram down here. And this is basically a contour that's trying to highlight combinations of catalyst concentration, temperature, and time that are likely to give us a good yield. And it just so happens, if I move the mouse cursor around here, just try to ignore the flashing, this particular position in this blue band that corresponds to high predicted yield, this is for 1% equivalent of catalyst, around about 8 hours, and dry ice temperature. So I'm just going to select that, hit apply, and now it has added the concentrations for the catalyst and the time and temperature for the reaction. So basically what we've done here is we've gone through this process and filled out the information on the scheme. So it's not quite an experimental procedure just yet, but we're getting way, way closer. Okay, so now I'm going to basically come back and go into a little bit more detail for all of these steps. So there's a huge amount going on under the hood here. Now, for any kind of modeling project, whether it's science or any other industry, the first thing we have to look into is availability of training data. And for chemical reactions, we're kind of given a bit of an awkward choice here. We have to choose between paying for the good data or taking our chances with the free stuff. Or there's option number 3, which is to create your own. And this is the choice that I opted for. I wouldn't recommend taking this lightly. You'll probably end up having to create your own custom tools for getting the curation rate to a reasonable level, and also finding all of the mistakes that are invariably get made. Nonetheless, I've been doing this for quite a while now. I won't say exactly how long, it's a long time. And I have collected up around about something on the order of 10,000 reactions, which are taken from mostly catalyst method design papers, at least initially. So if you're thinking about AI in general, you may be thinking, well, 10,000, that's not very many data points, and you'd be right about that. But the basic premise for this whole project is that if you have a relatively modest sized collection of data that is excellent quality, very, very information dense, covers a broad range of chemistry, and has a lot of the kind of structure activity diversity that captures the various trends going on, And if you build your models well enough, then you can create results that are quite competitive with absolutely massive models trained on huge amounts of data. And that's what I'm going to demonstrate throughout. I just want to say a little bit about the way that these reactions have to be captured in order to make these models work as well as they can. Basically, everything on the scheme has to be specifically identified, and its role has to be known within the reactions. You need to know the difference between all of your catalysts and starting materials and so on. It's very important that each and every component has a chemical structure that is not only present, but also correct. And by correct, I mean all of the atoms are there, either implied or drawn out. All of the atoms, all of the bonds, and everything has to work with a valence model that is compatible with all kinds of chemistry that are used. And that includes some fairly exotic coordination compounds that are really important for catalysts. This is something I could talk about for hours, but I will refrain from doing so, and suffice to say that it matters. Okay, so I'm just going to take a nerd out a little bit on the actual deep learning part. When people talk about AI these days, they're almost always referring to large language models that have been trained on absolutely vast quantities of data. However, we're talking about chemistry, and the most relevant data structure for chemistry is the molecule, which is essentially a list of atoms in no particular order, and those are joined together by bonds. Now, the technical term for this in the modeling world is a labeled graph, and that happens to be one of the fundamental data types that you can feed into a deep neural network. If anyone is actually curious as to how that works in practice, in a nutshell, you basically take all of your molecules, and for each atom, you feed in a single row. And so that's your first level of input. And then you stack together several fully connected layers for these atoms. And for each of these steps, you do the normal deep neural network thing, but you also add a graph convolution step, which means that for each of these bonds, you use those to share information between the adjacent atoms. And when you go through several layers of this, the atoms start to learn about their environment in the molecule. And then when you've done enough convolution steps, you then basically add up all of the vectors on a molecule by molecule basis. So instead of one row per atom, you've got one row per molecule, and then you can just push that through the network just like you would with a regular neural network. Just a note about some of the content that's being fed in. Most of the reactions that I'm talking about involve feeding in the reaction, and we do this as a single graph. So all of the inputs, all of these stoichiometric inputs and the stoichiometric outputs are put together in the same data structure, and they are labeled according to whether they're on the input or the output side. And furthermore, because all of these reactions are fully atom mapped, we also add a special kind of edge connecting these pairwise combinations so they can cross-pollinate at the reacting centers. And we also know which of the atoms are actually changing during the course of the reaction. And so we can label these specially as being part of the reaction core. And so basically this gives the training algorithm a really, really rich data source to start working on. It can immediately delve into looking at the actual trends that are driving the positive or negative effects, whatever it is that we're modeling, rather than you're just trying to get a handle on how reactions work in general. And typically we'll feed in that whole reaction alongside some number of other molecule structures, whether it's catalysts or solvents or one of the other various ingredients of a reaction. Okay, so back to chemistry. So when I showed you the demo, I just pulled out a pre-canned example, but there are lots of different ways of getting your starting reaction into the model. A good way is to sketch out your basic reaction in ChemDraw, and you can just use the clipboard to paste it in and start from there. Another way is you can paste in from other formats, like, for example, reaction smiles, and that's a popular format for tools that generate reactions programmatically. For example, retrosynthesis tools will often give you this data format. And as a fun fact, if you happen to have a reaction smiles description that has atom mapping within it, there's a special little trick it'll do when it comes to arranging the structure so you can see it on screen. It will lay out the product, and then for the reactions, it'll try to make sure that all of the torsion angles have the same match the product using the atom mapping information. And so it'll basically orient the whole thing so you can see everything lined up in just the way that you would like it to. And that's one of those things that seems like a lot of work for a nice to have, but it's actually really important for cognitive perception by chemists. Just a couple of side quests. I don't want to dwell on these, but if you only provide a reactant or a product, the recommendation engine will actually look through all of its reference reactions and try to rebuild the whole thing with just the information that you provided in order to make it match a reference reaction. Kind of a cool algorithm, in my opinion, and if anybody wants me to talk about that more, do say so in the questions so I can come back to it. Another side quest slide is if there are any missing reagents, these can be found by going through examples of reactions and looking for a reagent that actually matches on the left-hand side of the reaction, or the inputs at least. Now, the mainstream workflow for reaction recommendation typically starts at this point where we have all of the starting materials and the product, and usually not much else. And the first thing to do is atom-to-atom mapping, because that's really fundamental to all of the other algorithms. They'll make use of this information in order to build really precise and effective models. So this is kind of a busy-looking slide, but it's going to capture the idea that atom mapping for reactions is already quite complicated because you've got a lot of issues with symmetry and pseudosymmetry, but there's also additional levels of uncertainty. For example, the byproducts are usually missing at the beginning. Sometimes you have a missing reagent, and sometimes people have provided other structures above or below the arrow, and we don't know if any of these are actually stoichiometric reagents, so should we be mapping them or not? We don't know. And we also don't know what the reaction transform is, because that's kind of what we're trying to figure out by doing the atom mapping in the first place. So this is a sufficiently important and difficult problem that it's actually worth making an entire deep learning model just to solve this one. And so what it's doing within the model is it's taking everything on the input side and everything on the output side, and it's superimposing each of the atoms onto each other in turn and modeling whether or not these atoms are actually mapped. And so it puts that into the training algorithm. And with a lot of pre-processing and a lot of post-processing, it's actually pretty effective. And so it can work under some fairly adverse conditions. And that's a really useful prerequisite for the rest of these models. The next thing that we have to worry about is byproducts. Two reasons for doing this, really. One, I regard it as a need-to-know property of the reaction, even though it's usually left out of schemes when they get published. For example, if your reaction is emitting a strong acid or a strong base or a gas or something flammable, that really does need to be taken into account when you're designing your experimental procedure. But even a benign byproduct is still important, because you have to figure out how to get rid of it when you're purifying your compound at the very least. And so the way this is done modeling wise, the reaction information that we have so far, that you see on the screen on the left, is placed as the first graph into the model, and then the byproducts is added side by side, and these are trained up as basically, is this a byproduct of the reaction or not? And so it's a probability output. This particular example, it's very sure that the result is this boron compound. It's probably not something that you would isolate, but you're certainly gonna, those atoms have to go somewhere, and so that is something you're gonna have to deal with during the reaction. Quite aside from the actual value of knowing this before you do the experiment, byproducts are really important for bookkeeping, because when it comes to balancing the reaction, you can never be quite sure that you've accounted for all of the atoms unless you actually have all of the components. Balancing is, for organic chemistry, it's usually not too complicated, but it is made more difficult by the fact that the stoichiometry does feed into the atom mapping and byproduct prediction. So all of these three steps interfere with each other, but it's usually pretty straightforward to do it in a kind of brute forcing way, just try all the combinations. So for the most part, it's able to figure out how much of everything, get everything balanced, and get all the byproducts right. And that means that the housekeeping for the reaction is basically done, and we can move on to the good stuff. So speaking of that, the first one, as you saw in the demo, is the catalysts. Now, a lot of people who have tried to build models for reaction conditions have lamented the fact that most of the training data they have includes very, very few negative examples. And so, typically you'll get a lot of reactions that give you between 50 and 100% yield. I have two things working in my favor for this. One of them is that what I mentioned earlier is that a lot of the training data comes from catalyst method design papers. And if you've ever read any of these, the basic pattern that everyone follows is that the scientists will have found a way, an example of where a catalyst system works unusually well, and then they will explore the boundaries of that performance. So they'll find reactions where the performance starts to taper off and then crash down to nothing. So each of these papers is its own structure activity study. So I do actually have quite a bit of negative data. Furthermore, for a catalyst, yield really isn't the only metric that you are worried about. You want a catalyst to have as many turnovers as possible. So that means you're trying to minimize the amount of time. You want low temperature and low concentration, so the catalyst can do as much as it can with the absolute minimum amount of inputs. And so these four factors can easily be combined together in a score, which really spreads out the range of what we're training it on. So we've already got a lot of very rich information about the reaction. We have got the catalyst described as a structure with a valence model that works for all the inorganics. And we've got a broad range of efficacy for each of these catalysts. When it comes to actually providing this as in practice, there is quite a lot going on in the catalyst prediction step. The first one is the screening model, which is basically trying to decide whether or not you need a catalyst. And since the majority of organic reactions don't, that's quite a useful feature to be able to say, well, don't give you something that you don't need. So once it passes that screening model, the next thing it does is it looks for all of the reference reactions that share the same core transform as the reaction you're putting in. And it pulls out the unique list of catalysts for each of these and scores it according to the model that I displayed on the previous slide. And so these are ranked in order of highest first. And you may also notice on the screen there's a number in brackets, and that's an indication of the confidence of the score. And it's based on a Bayesian model that's feeding in structure fragments for both the reaction and the catalyst. And it's modeling whether or not that particular reaction was able to predict itself within a very narrow tolerance. So the percentage is an indication of the extent to which it is not only within the domain that it's trained on, but also a part of the domain that happens to have a very high recall. So it's just another useful metric that you can use for making your decision about whether or not to actually go and try any of these catalysts. Now, solvent prediction follows. It uses a very similar prediction method. One of the differences that because it's done after catalyst, it actually feeds the catalyst in, if any, so it can take that into account when it's picking the solvent, because catalyst solubility is important. One of the things you should notice about the screen is that there are a whole lot of glyphs on the right-hand side, and these are excuse me, green chemistry metrics. So basically you want to see a lot of green and not much red if possible. Now, this particular example is coincidentally quite interesting because water is actually ranked at the very top there, and that is of course, the ultimate green solvent. So it would be great if that was actually true. But as someone who used to be an organometallic chemist, I'm looking at that catalyst. I'm thinking that's not a water thing. I see metal centers surrounded by a bulky organic shell, and so my natural instinct is to reach for the nearest bottle of chlorinated solvent. So basically, if I was to see a model that told me to try water, I'd probably ignore it. And if a colleague came up to me and suggested that, I'd probably ask, well, where are your references? Well, just so happens that because all of these models are built from references, we have a DOI attached to each of the inputs. And because these reactions, both the candidate and the training data, are so heavily marked up with metadata, it's quite easy to come up with a similarity function that identifies the best exemplars that justify why that particular prediction is made. And so the recommendation engine behind the scenes, it's pulling out 3 or 4 references for each of these that is best tells you why it made that decision. And in this case, one of the references leads to organic syntheses. And if you're not familiar with this journal, it may very well be the most reproducible journal in science, as far as I know, because the referees will actually repeat every submitted synthesis. And if they don't get the same results, well, they don't publish it. They've been doing this for 100 years. I've curated 10 years of it, so only 90 left to go. Nonetheless, you can see from this example that the input materials are quite similar to our candidate reaction. And the catalyst that they're using in this case is something even more hydrophobic, even more bulky than the postulated catalyst. So, and they're doing the whole thing in water. So all of a sudden, putting on my scientist hat again, I find this interesting now. But because I hung up my lab coat a long time ago, I can't just go out there and try the reaction. But nonetheless, it does bring me to a bigger point in that the most useful possible predictions that a model can make is something that is both counterintuitive but also true. And those are of course, the things that are hard to believe are the ones we really have to work extra hard to justify to scientists. So finding references that show similar kinds of reactions, that's one really effective way to lower the barrier to convince experimentalists to go out there and spend actual time trying this out. Okay, so there's one model I'm skipping over. There's a model for adjuncts that is coming up. I haven't quite wired it up yet, so I'm going to jump to the last one, which is figuring out the scalar conditions for a reaction. Now, this model is the most information hungry of all of them that I'm talking about. It basically involves feeding in everything we know about a reaction. So at this point, we've got all of the components, the overall stoichiometric part of the reaction with all of the transform information, any catalysts, any solvents, any adjuncts, they all go in as graphs as part of the input process. And then the time, temperature, and catalyst concentration, if applicable, they're all fed into the model as well. And these aren't graphs, obviously, but deep learning models are quite flexible like that. You can put a lot of different data types in and then merge them all together. And then the final output for this model is the yield of the reaction. And so the way that this works when actually using it in a recommendation context is to sample various options for time, temperature, and concentration and come up with a grid of data points, and then project this grid down onto a 2D representation so I can draw a contour, and you can see some good places that are likely starting points for your reaction. So basically, you're looking for blue patches, and the way I've done this diagram, it's kind of a pizza donut representation, if you like. And so basically, each of these slices corresponds to its own specific catalyst concentration, and within any particular slice, the temperature increases as you go outward toward the rim, and the time increases as you go clockwise around it. So I wouldn't necessarily claim that every particular point on this overlay is an accurate yield concentration, but at least with literature spot checking, it does seem to be a very reliable way of finding a good starting set of conditions. And I should probably mention that I mentioned earlier that this is a particularly data hungry model. It didn't train at all when I tried it a couple of years ago. And at a certain point, the amount of input data that I've generated crossed over a threshold, and it actually, the scoring function of the model actually finally started to converge and started giving useful results. Okay, so that kind of brings me to the end of the single experiment story arc. So this idea of a complete reaction scheme, it's adding a huge amount of information that's really useful to add to the basic reaction. Of course, it's not an actual experiment, so you still need a chemist to figure out how to do it within the lab. But that is kind of a day in the life of a chemist. Most of my grad school research was working on a lot less information than that, and some of my reactions even worked. One way to think of these recommendations is kind of a piece of advice that's based on a very focused literature search. So it's basically using a lot of pre-digested information from very relevant literature articles and then applying that specifically to what you are trying to do rather than just one reaction at a time that you'd get if you were just reading through the literature. There are a variety of ways that we can, situations we can imagine this could be useful. And one of the more obvious ones is if you're new to a domain of chemistry, you can very quickly find out what people are doing, what has been shown to work in the past. And as I showed in the demo, this is a pretty quick process. It's not, even if you're using it for real research, you're not sitting there for a long time. It really is supposed to be pretty streamlined. But another more nuanced option is if you're actually already somewhat of an expert in the field. As chemists, we do tend to kind of develop favorite materials and techniques, and once we get really good at them, and sort of the barrier to trying anything new can get a little high. So it's always good to do a reality check just to see if there's something out there that will work better for what you're actually trying to do at this very moment, rather than just deferring to the classics. Even aside from providing useful information for executing an experiment, this idea of completely filling out the reaction scheme is really, really useful in terms of record keeping. So you probably noticed that the amount of information that is crammed into one of these schemes once it's actually filled out, it's a lot more information than people normally write out in a standard ELN. And so if you actually save this information, like put it into your ELN or export it back to ChemDraw and save it, you're creating a pretty valuable resource that's referring to your own science, which is usually more relevant than stuff out there in the literature. So holding on to that is going to make your own research actually provide a lot more value. Okay, so the last thing I want to talk about, and I think I do have time to talk about it a little bit, is this a very experimental project. It's totally not finished, but I think it is interesting enough to talk about nonetheless. And it's basically a take on the idea of design of experiments. So if you've ever read up about reaction optimization, you've probably heard this term before. In a nutshell, the basic idea is you define a bunch of parameters that encapsulates the optimal conditions for your reaction. And because that's usually results in a very large number of permutations, you're not going to do all of those reactions. But if you do the math right, you can actually get to the optimal results with a very small subset of the total number of possibilities by doing several iterations and making use of the information you get from each step. So the general idea of what I'm trying to do with this project is that design of experiments the methodology doesn't really help you actually figure out what parameters to use for your reaction, because you have to know that already and set it up. Now, with all of these recommendation models that I've been talking about, we do actually know quite a lot about most reactions. And so we have the option of proposing quite a few different parameters, not just simple things like time and temperature, but also catalysts that are likely to work well, and solvents and adjuncts and various other parameters. And so we can come up with a set of possibilities that are likely to have any probability of success. And then we can also treat the data with a bit more nuance, because these parameters they're not just a bag of marbles, which they're chemical entities that we actually know something about. And so, for instance, if a particular catalyst, for instance, tends to model well in terms of performance, we might want to weight that up and give it more representation in our first batch of experiments. And other ones which may still work, but we want to keep them in there anyway, but maybe we do fewer experiments involving those. And then there are other details, like basically we're trying to do a small number of experiments to learn as much as possible about what makes a reaction work well. And so you can imagine that if you were to swap ethanol for propanol, you'd learn a small amount about the reaction, but if you swapped it out for, say, water or benzene or DMSO, you learn a great deal more. So these permutations are not all created equally, and we have a pretty good idea of which ones are going to tell us the information that we want to know, because we understand molecules and we have a pretty good idea of what's going to happen in the reaction context. So the way the interface works, this is just a sneak preview. So if we feed in just a reaction, that's a way, and without any further constraints, that's a way of saying, okay, go through all of the literature information and propose an anything goes array of experiments. No, nothing is off limits. If we've seen it before, it's fair game. And so basically you'll get something that looks like usually a very diverse collection of solvents. You can see a lot of different structures that are represented. An even more diverse collection of catalysts, because this is basically everything from the literature. And if you check out any of these particular proposals, you can see that each one is a fully built out reaction scheme, just following the same principles as I've been talking about for the other part of the talk. And so this is basically a bunch of experiments which are fully marked up and ready to be basically converted into an experimental form. Now, this has not been done actually in the lab, because the number of high throughput experimentation robots I have in my lab is exactly 0. Nonetheless, the story isn't quite finished, because once the experimental data has been fed into the design engine, it actually changes the way the scoring and distribution works. So when initially, the way that it's arranging all of the options is by random sampling of all of the many different combinations, and then having a scoring function that tries to prioritize high yields using the yield model that I described previously, but also antagonistically, it's encouraging diversity of all of the reaction parameters that are variable. So you want as much structural diversity in catalyst and solvents and anything else that you're modeling. And so it's playing these off against each other to try and explore space, but in a guided way, to try to make sure that the good stuff is represented, but the things that might be good, even though it didn't predict, are represented as well. And so once we've actually started feeding in real experimental data, it changes the way the scoring works. So it defers to actual experimental results in preference to predictions that are made from a literature-trained model. And so basically the next round, on one hand, it's encouraged to propose reactions that are quite similar to ones that worked in the previous one. On the other hand, the diversity functions are pushing them away from each other and away from previously executed reactions. So you're still exploring unknown space, but you're kind of honing in on the examples that actually worked well. So as you might be able to tell, I'm actually quite excited about the potential that this has to streamline the optimization of reactions. And so I really will be excited to actually test this out in the lab. So that brings me to the end of the talk. The theme that's been running through the whole thing is that if you have a collection of data that is really high quality and information dense, you can do some pretty compelling and interesting predictions, as long as you focus on the you really make optimal use of that data. And so the state of the reaction recommendation engine really is a mature prototype, is what I like to call it. It's completely ready to be integrated in with the kinds of tools that people are using in the real world. And well, let's face it, any model is, no model in science is real until an experimentalist has taken some of these predictions and gone out into the lab and verified that they are actually useful. So prospective validation is the jargon term for that. And so this is part of an ongoing conversation, and a big part of giving this webinar is basically to invite you to participate in this conversation. All the reaction recommendation tools, they are actually online right now, but they are behind a password wall because, well, the internet is a dangerous place, as we all know. So I'm reluctant to open it up to everyone everywhere at the moment. But if you are interested in trying it out, you're absolutely welcome to do so. Just follow the survey link that you either have already or will receive soon. And we'd absolutely love to have your feedback, but if you just want to try it out and then go about your business, that's fine too. There's no commitment. So yeah, lastly, thank you for attending the webinar. And if you have any questions, I'd be happy to address them.
Thank you very much, Alex, for this very interesting presentation. We have several questions already popping up. So for those who are interested in asking their questions, please use the right side panel where you'll see a little icon with this question mark. So you click on it and then you can ask your question. So let me take you through the first question that I've received. So the first one is, so you've talked about a lot about catalysts. So the question is, can the tool work with reactions that don't require any catalyst?
Oh yeah, absolutely. So if you don't have a catalyst, it just proceeds on to the next part. So it'll recommend your solvents and then any other properties. So yeah, no catalyst is a valid answer. There's a certain amount of bias because I just happen to really like inorganic chemicals. So catalysts are particularly interesting to me.
I see. All right. Second question, how often do you update the model that predicts reaction conditions?
So it's done on a fairly irregular basis because you might describe the training data as boutique, high value, relatively low quantity. It actually doesn't take all that long to rebuild the reaction. So several hours or maybe overnight, just on a regular entry-level GPU is enough to retrain any of them. There are 7 or 8 models, so they're not always done together. But it's done whenever I have add an amount of data that I think is going to change the model or made any other modifications. So it's a fairly straightforward process. It's not too expensive in terms of performance.
Thank you. I have a question about, so there are two questions here. What application is this and how much is it to have full access? So I think, well, what I can say is that it's not part of ChemDraw application. So maybe it's a person who joined a bit late. It's not part of the ChemDraw application suite, but we thought you'd be interested, right, in trying the technology that Alex presented us. And maybe, who knows, in the future it will be integrated in ChemDraw, right? So that is typically the kind of discussion we like to have with you as users, is what is interested to you, what you'd like to have in the future of our applications in ChemDraw as well. So maybe, Alex, you want to complement that answer, right? How much is it to have full access? That's something you also sort of answered a bit, but maybe elaborate a bit more.
Yeah, to be determined. Right now it's a prototype, and so we'd love to get your feedback on it, but the actual commercial case for it is work in progress.
All right. Then the same person asked, so he or she is a master student doing synthetic and analytical chemistry and is wondering if it gives the reaction mechanism.
Definitely not the mechanism, but having the reaction fully balanced and fully atom mapped, it gives you a lot of clues as to what the mechanism may be. I mean, you've got all of the atoms that change state, so it's not a huge jump to go from that information to the arrow pushing representation of it.
Thank you. Following question is, could you tell us more about the body of data that you've used to train your models? What is the source of data that you've used, or sources, right?
So initially, it's basically probably about a decade actually of going through literature articles primarily with initially a heavy bias towards catalysts. So a Journal of Organic Chemistry and ACS catalysis are common ones, mainly because of this observation that there's a lot of good, bad, and ugly data for each one. So it's very suitable for modeling purposes with a specific bias towards catalysis. More recently, I've been trying to pad out the data without that catalysis bias. So there's quite a lot of papers that are and other sources that are in there specifically to make sure that all of the classical reaction types are well represented. So you're just going down a list of the 100 most popular reactions in named reactions in organic chemistry to make sure each of those gets a look in there. And then there's also some content from, if it's to pull in information from patent mining, not used as is, the time taken to actually fix these up is actually almost longer than actually curating it from scratch. It's brutal. And then there are a few other miscellaneous data sources where people have published content in a form that's almost up to the high bar that I'm setting for the input data, but needs a great deal of work, but can be partially automated. There's stuff like that going on. But anyway, the short answer is it's primarily directly from the literature.
Thank you. So that's the last question I had in the queue. Maybe give the attendees a bit more time to ask their question. 5 or 10 more seconds. If not, then we are going to wrap up and launch the survey so that you can, if you're interested in trying Alex's tools to predict reactions in particular, well, you can dropping a little message and it will be forwarded to him.
Yeah, and if anybody thinks of questions later, don't be shy. I'm very friendly.
We have 2 people raising their hands, so I'm not sure if we can take them. So maybe if you can, ask your question in the queue of the questions, that will be more practical for us. I don't see anything coming over. Okay, well then, thank you very much, Alex, for your time and for this presentation and the very interesting tools powered by AI. Again, if our guests of today would like to fill a little survey and liaise with you, they can do that with this, the survey we're going to launch immediately after I stop speaking. So thank you very much, everyone. Thank you for attendance and all your questions. And see you at next ChemDraw Connect that is scheduled in Q1 next year. Thank you very much indeed.
Bye.
Bye.